And today I am teaching you about heat maps. So, like, I'm live. Okay, great. Welcome. So heat maps are a super useful tool. You can use them to visualize high dimensional data and to cluster data into meaningful patterns, or you can use them for smaller data sets as well. And today we are going to be learning how to use two packages to make heat maps, pHeatmap and Heatmaply. And here on the U of T Coders website, just under the event for today, I have a link to the data sets we'll be using later on, as well as a link to GitHub repository that just has some of the material that I use to create this code along, and as well as the data set that we're using. So I thought what I would do just quickly is just give a little overview of what actually a heat map is. This kind of is something like what I would be using heat maps for. This is a heat map of gene expression, and samples would be along the bottom. So there's the gene expression value for each gene for each sample, and the values are represented by colors here. And then we have some kind of grouping or clustering that's bringing order to our data. So as a general idea, this is from a blog called You Probably Don't Understand Heat Maps. This is a picture of gene expression, and we have two genes that are highly expressed, the red and the black, and two that are lowly expressed, the blue and green. Now, that's fairly obvious, but what we're probably more interested from a biological perspective is the genes that are going up and down at the same time. We're interested in pulling out these patterns in the data. So how do we do this? Well, first we need to calculate some kind of distance metric. How do we tell whether samples are similar or different? So if you're looking at the red and the black, you could calculate the distance between all of these points. You could sum them. You could take the maximum or the minimum. You could take the mean. And you could do that pairwise for all of these samples. So there's a whole bunch of different distance metrics that you could use. It really depends on your data. So this is an example of just taking one distance metric, the Euclidean distance. And if you look along the bottom, I or L, 2 and 1, have a value of 5.6 as their difference, and that's the smallest distance, so they'll be grouped together. And then the next smallest distance is H1 and H2, so they'll be grouped together. And then those two groups will be paired at some point. And so the way they get grouped is through hierarchical clustering, which is basically looking at those differences and picking the most similar pairs iteratively until there's only one value left. So here, the way that it's clustered, I1 and I2 had a difference of about 5. They're clustered at the bottom. There's a long branch of almost to 40. And then H1 and H2, which had a distance value of about 28, are on the other side. Now, it's important to know that every time something is clustered like that, it's completely arbitrary, whether it's on the left or the right. So those can be flipped. So I1 and I2 can be flipped, H1 and H2 can be flipped, and then the entire kind of tree can be flipped. So if we ended up clustering this, we would end up with, these are the values we just talked about being clustered here. And then I1 and I2 had lower values, so they're a lighter color, and H1 and H2 had darker or higher values, so they're darker color. And this is telling us which samples are kind of more similar, but it's not telling us how those genes, the expression was moving over time, the kind of shape of the overall trends. So in order to do that, you need to actually look at how similar things are. So if you take the correlation, because H1 and H2, one's moving up and one's moving down, they would be distinct from each other and be at have opposite correlations. Whereas H1 and L1, which move up at the same time together, would then have a correlation of 1. So in order, we have to plot distances in heat maps. So the distance is just 1 minus the correlation. And then we would end up with a matrix which we could plot. And then when we look at the dendrogram for this, they're now at equivalent levels. H1 and I1 are together. So we're going to be looking at this and creating heat maps. And you won't see any of this. This will be behind the scenes, but it's what's going on. Just essentially, you have your data, you have to calculate a distance metric, and you have to cluster your data in order to get these patterns out of your data. So let's go into R and load Heatmap. And load our data sets. So the first thing we can use is read.csv. Yeah. I just want to keep part of the screen for the plot. Can you see that, or larger? Okay, so we have the row names are equal to 1. I'm just using base packages here to keep it simple. And then we have also annotations for our rows and columns. So we'll look at all of this as soon as we read it in. Did everyone manage to find the data set? Yeah. And then we also have annotation for the columns. Okay, so when we look at the data set, we have genes which have an expression value. This has already been compared to some kind of control condition. This is like a log fold change value, so it's already been normalized and everything. And then we have patient data. And then the annotation that we have available is we have 4 different pathways that these genes could be in. There's 100 genes and 4 pathways. And then we have whether the patient has been exposed to a drug or not. X equals 0 is not, X equals 1 is yes, and then whether they have T cell or B cell cancer. Yeah, the row is just, it's just like a biological process. It's not real data, so it would be like pathway 1's DNA repair, pathway 2's like carbohydrate metabolism, something like that. Okay. So in order to make a heat map, we can just take this data right away, kind of plug and play. And this is a large data set. Should come back in a minute. So starting off, we get those dendrograms we were looking at before. There's been clustering of rows and columns. We're going to look at the data in a second. We'll change the fonts and things so we can actually look at it. But these are genes, these are patients, and they've both been clustered here. And the defaults in Heatmap are that the clustering, you don't need to type this if you don't want. This is the default argument. I just want to emphasize that the clustering distance is Euclidean. So that's a short path distance, and it also takes magnitude into account. So by default, both rows and columns have been clustered. And the clustering method is complete linkage. So that's kind of the defaults for Heatmap. And we'll just start off by changing the font size so we can see what's going on here, maybe a little bit. It'll take a couple seconds for this to reload. And while the default is to cluster by rows and columns, if I just wanted to group genes according to a pattern and just hold whatever pattern the patients had as stationary, I can say cluster rows true and cluster columns as false. So I'm just tab auto completing a couple of those things. So in this case, we can see that we've got these kind of groups of genes that are clustering together in different patterns, and then some that look like it's completely random. And if you wanted to look at it the other way, you could, of course, switch that around too. So if you want to look at patterns that are just in the patients and hold the gene clustering constant. And then you won't have a dendrogram on the side that you mark clustering.
I don't understand what is the rule of columns at rows. Why do you need to say clustering distance? Why do you need to define both clustering distance?
Like here, the default's Euclidean, so you don't have to.
So why do you need to define it for both rows?
You don't have to. I just wasn't deleting it because I'm changing the what's being clustered. So right now, cluster rows equals false. So I could delete the clustering distance rows as Euclidean. I don't need that in my argument. I just keep updating this particular function call.
Can both of them be true? Can both of them be true? Cluster rows
Be two?
True.
True, yes. Yes, so the default is true. And we'll mostly be working with default with cluster rows and columns being true because you usually want to pick up both of those patterns. But of course, it's hard to kind of tell what's going on without your annotation. So the nice thing about Heatmap is that you can add your annotation to this as well. So there's an annotation row underscore. And so I can just add, I actually named my annotation row. So I'll just show that before I put the columns on. So there's pathway as a little legend here, and it's 4 different shades of green. So we can see that along here that some genes that are in, say, clusters 3 or 4, which is the darker greens, are clustering together, and pathways 1 and 2 are clustering together as well. So we can add the annotation for our columns. And then up here, we now have whether the patients have T or B cell cancer and whether or not they've been exposed to a drug. So in some cases, it looks like treatment is having a large effect because those are the groups that are clustering together. And then you might say that this dendrogram here, which is treated patients, are having high gene expression for cluster 4. Because it's red, there's a red pattern there. So you can kind of start to pull some of these things out. Heatmap is highly customizable. This dendrogram's a little bit overwhelming once it's clustered. You might just want to remove them, in which case you could say tree height equals 0. Give yourself a little more space. You could add a title. I think it might be name. and you can change the general font sizes if you want. So I could make my title font size is kind of like the base font size. So I could make this 6, and then that will be kind of the font size for my title and legend. And then I can have the font size for my rows and columns, which are the names. I can have them be smaller. So now we have the title, and the stuff's a little bit larger. We could remove the legends if we were interested in doing that. There's annotation legend, and I would just put false. Okay, so let's see. One of the things that's kind of useful, I guess we'll make a subset of the data just so we can see this a little better. I'm just going to make a subset of rows 1 to 5 and 55 to 60. That's just so I have a couple different phenotypes or patients in there. And I'll just take columns 1 to 5, 20 to 35, and 55 to 60. That's Matt. Yeah. Okay. So I'm just going to change this here. Now we have something we can see a little better, although I guess I can change the font now that it's zoomed in a little bit. 8. Okay. So other things that we might want to do, we could actually display the numbers if we wanted, what the correlations actually are. Small. There's a font size number as well. And then one other thing you might want to do is to be able to kind of export this data back in the ordering that you got it in. So you can save the graph into an object. So I just saved it as H, and it's actually a massive data structure if you do stir on it, but I wouldn't. It'll keep scrolling and scrolling. But you can actually get the order of your rows and columns by taking the data structure, saying tree row, and grabbing the order, and that will print out the list of the order of the rows. You can do that for columns as well. So you can end up subsetting it in the order that you want and saving it to a data frame or something else to export by just doing this. So now this is my ordered data frame, and I could write this to a CSV file or something like that. If you end up putting this back into the pHeatmap function, it will look exactly like this. The order, anyways, not all the pictures. Okay. So you can change all of the clustering distance options. I don't know. How many of you have made heat maps in R before? Is anyone familiar with distance objects or clustering objects? No? Okay, so there's a variety of the clustering object dist is a pretty standard object. So I'm just scrolling through the help file right now. And an hclust object here. So first you calculate the distance and then you cluster. And you can cluster according to all these methods. So ward, single, complete, average, median. For the heat maps that I do, most people use complete or average. The distance here, if you wanted to instead just have a Pearson correlation or something, you could put correlation in here. So you can customize any sort of distance metrics or clustering metrics that you want, pretty much. But if you don't know what you're doing, you can stick with the standard unless you have something like binary data, then you need to definitely look into something else. Okay. Trying to think. Oh, colors. You can change colors. You can make your own palette by just specifying whatever you like. I'm just going to say light blue, cornflower blue, navy blue. And you just add color equals for palette. So now everything will just be a blue color. Oh, I saved that to H, so we'll print. And now everything's blue. If you had the Viridis library open, you can also put in some of their palettes here. There's a Viridis palette, and then you say option. I don't remember the names of all the palettes right now. There's one called Plasma, I know, and then say maybe 6 colors. You can use that. I think I wanted. It's it's right now it's been clustered. A distance metric's been calculated and it's been clustered. So for P heat map, you don't have to do that step separately. For some heat map packages, you need to calculate that first and then input it. But here I've also transposed the matrix ahead of time. If sometimes you'll see that it's transposed, but I already have it oriented in that manner. That's basically just because this random sample that I've taken isn't that representative, I guess. I probably should have picked.
Even for math, even when we put math, it was not that all the red ones were in one block altogether.
Right, because it was also clustered by patient, though. Because it's both directions and
So the heat map that we see, not those annotations, like those whatever it is. But the heat map that we see shouldn't be in blocks of same colors. The numbers in between, it's still the distance.
The number is the gene expression number. It's not the distance number. Yeah.
Visualize the software itself.
I
heat map, if you put it in H, do we have the distance matrix?
If you look inside the H object, yeah, it will be in there somewhere. Yes. Kind of like scared to do stir on this right now. Oh, so that's like subsetting. So it's this is a giant like list object. So you could subset it like
in H objects, we want to column K.
Yes, they're all in H, and then you can go further deeper into that by going with the $sign again. You can also subset things with double brackets if you're used to subsetting lists that way. You can do it both ways. Yeah, I mean, so here it says it's a list of 4, but you can see it's quite large. So there's rows, it has all your heights, methods. There's a lot of information in here, and this is just the first list. There's like 4 of them, right? It's still nested. See how nested that is? So like, it's a little ugly. I would actually probably just calculate, like if I was interested, I would probably calculate the distance. The distance is 4 sub and just plot this separately. And you can also do your H clust on this, so the clustering, and get the order out of this. So if you wanted to cluster the distances, I would do it by that way. And you could plot that as well. You can also do just like basic correlations with this. So you could just say 4, that's your correlation test, and put sub in there, and this will be the correlation of your patients against each other. And again, you could add annotation back on. So that's another thing you can do. Since we only have 10 minutes left, I'm just going to quickly show you an interactive version of a heat map. So this is with Heatmaps. And again, this, I would not use this for your basic heat maps. I would use Heatmap because it's really simple to use, and there's also another package on top, or that has used Heatmap as a wrapper, called Heatmap, which you can add even more annotation details using. So I would recommend you look into that. But this is really cool if you are having to give a lab meeting or a presentation or something like that. So this is an interactive heat map, and you can hover over the values and actually see, okay, that's what patient 55 was doing with this gene. And you can make some nice delineations. So what I mean by that is the dendrograms, they're all kind of, you know, they're all black. It's kind of hard to look at. But if I go kcol and I say 4 and k row 3, I can kind of group those into different colors, and it makes it a little clearer to see these groups. And then that's kind of nice. Also, yeah. Yes, you can save it. There's a special save function so that it will still be a interactive object. And the other thing you can do is zoom in. So this is crazy, but say your PI is like, what is this yellow segment? It'll take a second, but then you can like zoom into that. Yeah, and then you can take a download as a PNG, but there's a better function. There's a saving Heatmaps function. I forget what it is right now, but if you look it up, there's one that will. Actually, it might even be the same function. Anyways, you can look it up, but yeah, you can save it to an interactive file. So well, this one won't save it as an interactive one. I think this might, but there's also a chance it will crash R. So just save your work before you try it. So I'm not going to try it right this second in the live demo. But you can also once you add the annotation tracks here, I haven't added them yet, but you can also highlight and see what group everything's from. So that's cool. And then the other kind of functionality that Heatmaps has is it has some built-in functions to normalize or percentize your data. So if you want to say what is the largest gene value in each row or something like that. So if you look vertically down these columns, this is basically saying like, if I'm looking at this yellow, it would be like 95% of values are less than this value. 50% of values are less than this value. So this is the highest value for this patient. So there's a percentize function, there's a normalize function, and these are kind of built in with this package. So they'll each end up representing your data a little differently. This has put everything on a scale of 0 to 1, but in a way that they all retained their initial distribution. And so there are some different options for that you could look into. And these things can also, you can make other color palettes with this too. You can do different methods of clustering with this too, but it has a lot of the same defaults. So I think we'll probably wrap up on time. That's always fun. Yes.
Thanks for that presentation. The part that I still struggle with are the forks. What is the connection to what?
So it's connecting the most. So you calculate the distance metric, and then it's going to take the two samples that are closest to each other in distance, and it's going to put them beside each other. It's going to create a branch so that those two things are next to each other. And then it's going to say, okay, what's the next most similar thing to these guys? And then, so
For example, G60 is closest to G60, patient 60.
yeah, so these would have been calculated as the most similar to each other. So a branch would have split here, and then these would be treated as one unit. And then the next little closest pair.
That means gene 1 and 4 of patient 21 are closest in distance. The ones that you were comparing.
Yes, yeah.
For actually for all
One
the
and four.
patients, right? 1 and 4 for all patients.
Yes, because this is clustering by row. So those genes are closest in general. And then these patients are closest in general.
Oh, remind me again what the distance was.
So the distance is here, where Euclidean distance. So this would be a short distance between these two values, and it gets progressively longer as they're less similar to each other.
The Euclidean distance of the vector. So,
Yeah.
So gene 1 over all the patients is the vector of numbers, right?
Okay.
It's the vector of numbers that is in that. So one row, one vector. So you have one vector, and you have gene 4, another vector. Two vectors have a Euclidean distance to each other.
Oh.
That
would be the
they're being subtracted from each other essentially, and that has the shortest. Yeah. Cool.
I tried the export function for HTML. It does open the document.
Woohoo! Okay, stop the Google Hangout.